In the last class, we did material objectivity, right? And what we found out was that for all materials, W of F has to be equal to W of QF. And this holds for all Q in SO3 for all rotations. Okay, so this is called MO. And we said the outcome of this was that A and B is automatically satisfied. And this also means that W of will be equal to some function sigma of U only, isn't it? And then we said since it is same as sigma of square root of C, so it is equivalent to function, let's say phi of C, C, and we know that C, the right course contains all the information of the strain. All right, so this makes kind of sense. This kind of makes sense, and so we are today going to learn another very important topic, which is called material symmetry. And I don't think you will really do this in your continuum mechanics course. You have learned, for example, there are materials which are isotropic, then you have materials which are orthotropic, right? You have heard about them. Similarly, you can have transversely isotropic material. So what exactly they are? So for isotropic material, let us say you have this body and you are at a point, say big X. And if we, let us say, stretch the body along this line, at that point, somehow you can, if you allow the body to stretch, or if you stretch the body, then there will be some stress generated in that direction also, right? Say if this is X direction, so you apply epsilon xx, which induces sigma xx, isn't it? Likewise, you can again think of the same body, and at the same point, big X, but now say you are applying stretching in the y direction. So you are applying epsilon yy, and this is going to generate sigma yy, isn't it? It might generate other stress components also. And if it's an isotropic material, then we know that if epsilon xx is equal to epsilon yy, then sigma xx will also be equal to sigma yy, isn't it? This is what we know about isotropic materials, that the response of the material is same in all the directions. Okay, so here we did it just for x and y, but you can stretch in any arbitrary direction, and the corresponding stress that gets induced will be the same. And sometimes they also say that material properties are independent of the direction. Okay, so now you see it is just a property at a point that material properties are same in all the directions, or the response is same in all directions. The property can still vary from point to point. Okay, so I'll just make a remark that property, the material property, can still vary from point to point, in which case they are called non-homogeneous material. Okay, so a non-homogeneous material can also be isotropic. All right. So this is a confusing point for many students. When we ask them in an interview, they say that if it is isotropic, then it will also be homogeneous, but it is not necessary. The property can vary from point to point, but at a point it has to be the same in all the directions. Then we say it is an isotropic material. And then how about transversely isotropic? For transversely isotropic, there is a unique direction. So there is a unique direction. So let me write down. So there is a unique material direction, which is also called principal material line. And the property, it has got some unique value in this direction. But for all directions perpendicular to it, for all directions perpendicular to it, their properties are same. Are same, but different from that unique direction. Let us say this is E, but different from E in all directions transverse to E or perpendicular to E. So that's the transversely isotropic material, and you can now see why we call it transverse. So there is a unique direction, and transverse to that direction, it's isotropic. It's the same in all directions transverse to that unique direction. Therefore, we call it transversely isotropic. And then you also must be knowing about orthotropic material. Okay, so this is something coming from physics, and also something that we have seen our undergraduate course. But we want to make this concept more rigorous from the point of view of finite elasticity. And this comes under the topic of what is called material symmetry. Okay.
Sir, what factor is it that determines that which material will have isotropic properties and which will have orthotropic properties? Or
Yeah, that's a very good question. It all goes down to the structure of the material at micro or nano scale.
Sir, can you also give the example for each kind?
Um, yeah, for example, tungsten.
Yes,
So
sir.
they say that tungsten is isotropic at nanoscale, a tungsten material. So the if you look at the lattice of a tungsten, then it has the same property in all the directions.
Okay.
But or just think of, for example, a body centered BCC lattice, body centered cubic lattice. Okay,
Okay, sir.
so you go along. So it has three directions along its face normal, isn't it? Along the face of the cubic, along the of the cube.
Yes, sir.
The property of this for tungsten is the same in all the three directions,
Okay, sir.
along those three directions. And it turns out for linear elasticity, just for linear elasticity, the property is the same in every other direction also.
Okay.
Now, if you think of a hexagonal hexagonal closed packed lattice, HCP lattice, so you know that it has got one axis and then there is a hexagon in the plane perpendicular to that axis, right? So those structures are not isotropic by nature.
Okay.
If you have a material formed by HCP lattice, then it will not be isotropic. But then, it's also that although at nano scale, the crystals have got those anisotropic structure, even if it has got an isotropic structure like SCP, but we are looking at a material. The current description that we are talking about is at continuum scale, which is kind of macro, macro scale. So from nano to macro scale, lots of things happen in the material. At nano scale, we see the crystal lattice. You go to micro scale, you start seeing grains of the lattice.
Yes, sir.
And then, if the grains are randomly oriented at micro scale, then overall it has the effect of making the material isotropic at macro scale. You see, maybe I can illustrate it through figures. So suppose
Sir,
that at, yes,
sir, when we talk about this BCC cube, then
yes,
like we have this three directions. So two will be along the face and one will be along the diagonal.
no,
When
no,
we
no. I
consider
meant,
this,
yeah, let
the
me draw the
perpendicular. Okay, sir.
picture. So body centered, no? So it has got atoms at the corner,
Yes, sir.
and then there's one at the center also, right? That's body centered.
Yes, sir.
So because of the structure, you can imagine that the property in this direction, or in this direction, or in this direction, if I say X, Y, Z, they will all be same because crystal looks the same if you view the crystal from any of the three directions. But of course, if you look at
In
the crystal
diagonal.
from this direction, it does not look the same, isn't it?
Yes, sir.
But it turns out if the property are same in X, Y, and Z directions, then it will also be the same in this direction also, or in this direction, or any other direction, as far as linear elasticity is concerned.
Sir, is this observation that if it is same in three orthogonal direction, it will be same in other direction? Is it experimental result or something
Yeah,
like that?
if the properties are same along
Sir, sorry, but your screen is not visible.
in any direction for linear elasticity, or for linear stress strain relation, if you talk of non-linear stress strain relation, that means if you strain it really a lot, then the property will start varying. even if the property are same in xyz, it could be different in an arbitrary direction if you strain a lot. If you are straining very very small, so that you can approximate the stress strain relationship as being linear, then the property turns out to be the same in all the directions. Okay, now this is, so you had a very nice BCC lattice, but suppose you have a HCP lattice. Okay, and then you have many more. So you can see that this is one unique direction, isn't it? But this is, you are seeing at nano scale, having this unique direction. But at micro scale, you will have grains, each of them but being oriented differently. The grains are not all oriented in the same direction. So this is at micro scale. So you have grains. Now if you go further down to macro scale, then it looks like a homogeneous, homogenized because of the randomness. So grains oriented randomly. So at the macro scale, it looks homogenized. So it becomes isotropic because the grains are oriented randomly. So you can see that the same material, it is anisotropic at nanoscale but isotropic at the macro scale. So here it is anisotropic and here it is isotropic. It all happened because at the micro level the grains were oriented randomly. But if the grains are not oriented randomly because of some reason, let us say you apply electric field so that the grains start orienting in a particular direction, then you can change the material from being isotropic to anisotropic. So you can see that that's how you can tune a material, by applying electric field or magnetic field, or even by applying mechanical forces. You can change the structure of the material at micro scale so that at macroscopically it looks something else. Okay, so anyway, so these are the origin of the material being isotropic, anisotropic, or whatever.
Okay, sir. Sir, if at nano scale a material is anisotropic, at micro scale, because of its randomness between the grain and grain structure, we can say that it is a homogeneous material and it can be isotropic, right?
Yes, yes.
Okay, sir. Actually, this I was thinking when I was reading a paper related to brain tissue. So they tested in three directions. So they were telling that although the microstructurally there is lot of difference in three direction, but like they were getting like almost same properties. So they were telling we can consider it as isotropic.
Yes, yes, yes.
Okay, sir.
It's because at the micro scale there may be some random element of material which is overall making it isotropic at the macro scale.
Yes, sir.
Okay. So anyway, so this is a digression from our original topic. We just want to see the material at continuum scale, which is macro scale. Okay, macro, MACRO. Macro is continuum scale. And we are talking about the theory of material symmetry at continuum scale. Now, before doing that, let us understand a particular deformation and then I will introduce this concept of symmetry. So think of a material, and here's the reference configuration, and you subject it to some deformation f, okay, so that it changes like this. And think of a point x naught here. Now what you do is, now rotate this material and then think of another deformation, so that you first rotate the reference configuration by some rotation big Q and about the point x naught. Okay, rotate it about the point x naught. So when you do it, it will perhaps look like the following. Okay, so you have rotated about x naught. So in going from here to green configuration, you do rotation q about x naught. Okay, and since it is rotation about x naught, the point x naught remains at the same location. And then you apply the same deformation map as earlier, which is that small f. Now can you imagine what will the final body look like? Let me make this one a bit different. So in this case, in the second case, can you think of what will the final body look like? The shape, will it be same as this one, or it will be something else? What do you think? So to answer that, of course, we have to understand how we are applying the same deformation map. So the answer turns out that it is not the same. It will become completely different. You see, this is slightly different than the way we did in objectivity. Can you recall, in objectivity, in the second case, we applied the same deformation and then rotated the material, isn't it? But here, we are first rotating, then applying the same deformation. So I'll just make that remark here. In MO, we first apply F and then rotate. Whereas for material symmetry, MS, we first rotate and then apply the same F. So anyway, let us track the different points of a material for the two deformation process. So in the first process, when we have only applied small f, so any point big X will go to f of x, right, through that deformation map, and it is some arbitrary deformation map. In the second process, a point x, it first has to rotate q about x naught. So can you think of where will that point big X go if it's a rotation about x naught? So it's going to be big Q into x minus x naught, because it's rotation about x naught, plus x naught. Will you agree with this?
Yes, sir.
And then we are applying the same deformation. So that means the point big X, which has now moved to another location, shown by this thing here. Now it will undergo that F. F will be now applied to this new location. It will be of the new location. Can you see what has happened? It's like when we say it's the same deformation, that means the deformation that we are applying, it's simply taking a point from the body and moving it. And it is such that if the point is at the same spatial location, then it goes to the same final location. So, see, for example, this point big X, if it is here, okay, so this goes to somewhere over here. But once the body has rotated, there is no point in the body which is at big X now. Okay, so no point of the body will go to this point over here. But where will it go? This point big X has come first over here, right? Maybe think of it as an intermediate configuration. Let us say big Y. And then you have to apply deformation map, assuming no rotation had occurred, and apply the same deformation map. So you apply F to Y, and so it will go somewhere. Let me make it a bit more clear. So suppose there is a point big X1 in the red configuration. Now you see, when you do rotation about this X naught, then big X1, it's going to rotate and maybe it's going to come over here. It rotates like this. And this will be the green point. I denote by big Y1. And you see that big X1 has gone to big Y1, but originally there was some other particle at big Y1. So let us say the particle which was at big Y1 was actually X2 in the red configuration. So when we say we are applying the same deformation, it just means that f of X2 and f of Y1 will be same. So what this means is that f of X2 will be equal to f of Y1. Okay, maybe I can make the right thing, everything as green. So I have to also change the final configuration, because some points are at least matching. It's not like they are fully not matching. Some points are at least the same. So I should make it now I draw it with maybe a different color. Let us say green. And so you can see that big X naught remains at big X naught. So big X naught will go to the same point finally. So maybe with a color, say black, yes. So if big X naught has come here, then for both the configurations it will be at the same point, and but the total configuration will be something else. Is that clear to you? What do you think? Is it clear to you guys? What is happening here? So this f of big X naught, and this is also the green one, f of big X naught, because X naught did not change due to rotation. Both are same. Both points same place. But for a point big X1, big X1 may have come over here and in the first process, but in the second process, big X1 has gone somewhere else.
So
So
without the
this is
exception of x naught, no other point maps to the same in both configurations.
this is f of big X1 and this is f of big Y1. Yeah, now tell me what you're saying.
So without the exception of big X naught, no other point maps to the same place in both the configurations.
Yes. Well, it depends on the deformation map app. It could be that deformation itself, some other point also get mapped to the same location. Big X naught certainly gets to the same location. We can't guarantee for any other point. Except for big X naught, we cannot guarantee for any other point. Okay? So it's like, in the second process, when we are applying this deformation map F, the person who is applying, he didn't know that the body has actually rotated. He thought that okay, it's the same body. Let us just let us move it somewhere in the same way as earlier. Is that clear to you? To everyone? So physically, it means that in the first process, so you have a lab, you have a body, you apply a deformation to the body, then in the second process, you have the same body, but some other person comes and he rotates the body while you are gone out of the lab. Some other person comes and rotates the body, and then you come back to the lab, but you didn't know that okay, that person has rotated the body, and you apply now the same deformation as applied earlier, but you are unaware that the body has actually rotated. So obviously, because of this rotation which you are unaware of, the final configuration of the body will not be the same as in the first process.
Sir, is there any reason that why in the study of material objectivity we are following that sequence of operations, and in this symmetry we are following first rotation and then deformation?
Yeah, there is a reason, of course. See, objectivity always holds. For
Yeah,
objectivity, why did we apply rotation later? It was because we wanted to use this physics that if you rigidly rotate a deformed body, the energy does not change.
Yes, sir.
So therefore, we had to apply rotation afterward.
Yes, sir.
But here, we cannot apply rotation afterwards because we are doing a different concept now. See, what is happening, I'll tell you why we are rotating first. Just need to hindrance from someone. Someone's mic is on. Yeah. So why we are rotating first? It's very simple. We just go think of the isotropic body. Just think of a circular isotropic body, and you are at the center of a point, and you apply load, let us say, in this direction. In the second case, it's the same circular body, but think of first rotating. So you have, let us say, lines E1 and E2 engraved in the material. So when you rotate it by 90 degree, E2 comes here and E1 goes here. So this is rotation by 90 degree. And then, as I told you now, you have to apply same deformation. But and you are unaware that it has actually rotated. So you will again stretch the body in along the horizontal line, right? And if it is isotropic, then the response that you will get will be the same in both the cases, isn't it? The stress, if you measure, it will be the same in both the cases. So that is why we want to first rotate the body and then apply deformation. Is it clear to you?
Yes, sir.
Okay, anybody, if you can't understand, please ask me. Well, anyway, this is not a nice example because I chose a circular body which, when you rotate, it looks exactly the same because this body has also got that symmetry. But this concept can be applied to an irregular body also, just like here. See here, it's an irregular body, you rotate, so at x naught, the directions have changed, isn't it? The direction intrinsic to the body has changed at x naught, and now if you think of applying deformation at x naught, and if it is isotropic, then you will get the same response. Okay, so we are now trying to formalize that through mathematics. So now you can see this is the first process and this is the second process. All right. Now let us try to find out what is the total deformation gradient in the two processes. All right, deformation gradient.
Hello, sir.
Yes, hi Niranjana.
Sir, so you're telling that if it is isotropic, in both the cases, we are able to get the same configuration or like the same dress, like
Not the same
by response,
configuration,
human
same
configuration,
response.
right?
The response will be the same.
Not is that? Do you mean the configuration or like at that point, like whatever the stress and everything is coming?
No, I meant the response will be same at that point.
Okay,
The overall
mm,
configuration of the body is obviously not the same, right? You can
okay.
see.
So only the response is the same, but like the deformation then also will never be the same, like the deformation.
Say again, what was your last sentence?
So if in case it is an isotropic, the response will be the same, but in that also the final configuration will never be the same. It's different.
Exactly. The final configuration of the entire body will not be the same.
Okay, sir. I had a small
Okay.
confusion. Thank you.
Yeah. Okay. So this will become more clear as we work on it. So now look at deformation gradient. So for the first process, if I say it by F1, big F1, then that is simply gradient of little f, isn't it? And that I denote by big F. For the second process, what is going to be big F2? So that has to be del F, and inside you have Q into big X minus big X naught plus big X naught, and take the derivative with respect to big X. Isn't it? That's what you have, big F. Now let us call this thing inside the bracket, this one, as big Z. So F2 ij, that's simply del fi over del f, let zk into del zk over del xj, right? We can write it using chain rule. Now what is zk? So use the formula of z, what will be zk? The kth component, that's q k l into xl minus x naught l plus x naught l. Agree with this? So if this is the case, what is del zk over del xj? So that's going to be 2kl into del xl over del xj, which is jl, which is simply qkj. Okay, so we can come back here and write that this is del fi over del zk, and this has to be evaluated at z into qkj. And if you think of the tensor form, then big F2 is then, you see, this is the big F, but at Z into big Q. So that's your F2. And whereas F1 I'll write again, that was equal to big F of big X. Can you see this? So this is what the deformation gradient is. Now if you also think of what is going to happen to energy, so W1 at big X, so energy, so you are talking of energy density at each point. So W1 for process 1 is simply W of F2, isn't it? F2, sorry, F1, I'm sorry, F1 at big X, which is W of big F at X, right? Whereas for the second process, W2 of big X is then W second deformation gradient, F2 at big X, which is actually W or big F at Z into big Q, right? So you can see that if you look at different points in the body, the deformation gradient which gets induced, they are completely different in the two cases. You can see that at a same point you have two different deformation gradients. It is not just the difference of q, there is also a difference in the argument here. So big F will also be different. In addition to q, there is a difference in the value of big F also, because it is being evaluated at two different points. In the first case at x, in the second case at z. Isn't it? So therefore, the energy that will get stored in the body at different points will be completely different. Contrast this with the objectivity. In objectivity, the energy stored at corresponding points were the same, isn't it? But here, the energy stored at corresponding points are not the same. And you could also see that the overall configuration was also different. And even locally, globally, the overall configuration is different, and even locally. So I'll just make that remark here. Globally, the overall configuration is obviously different. But even locally, stored energy density at corresponding points are different. You see, there is quite a difference here. Not just globally, but even locally, the energy stored is different. But concentrate on the point x naught itself. Just at x naught, but concentrate at x naught only. So what is F1 at x naught? That's simply big F of x naught. What about F2 at x naught? That's going to be big F of z naught into big Q. Now let us see what will be z naught. Using this formula, have a look at this formula. What will be z naught? When you put x equal to x naught, what is z naught? Anybody? Pulkit?
X
Yeah,
naught.
x naught, right. So this is same as big F of x naught into big Q. So you see at point x naught, at least these two are same, right? There's just a difference of big Q. At other points, these were also different, but at x naught, at least these 2 points are same. All right. Now, we will now come back to physics. Let's look at that deformation again. And suppose that, even after rotating this body by big Q, if the material is such that the response at x naught remains unchanged. So what all we are doing is, when you rotate the body, the intrinsic direction of the body at x naught, they are changing, and then you are applying the deformation in the same global direction. And if the material is isotropic, I mean not isotropic, I mean to say if the material had symmetry, we would say that the energy stored at x naught will be the same in the two processes. So what material symmetry tells us is that if this rotation q is such that the energy stored at x naught is the same in two processes, then q lies in the symmetry group of the material. Let me write that down. So the statement of material symmetry is that according to MS, if the stored energy density at x naught is the same in the two processes, then we say that Q lies in the symmetry group of material. Okay, and so this simply means that W of F naught is equal to W of F naught into Q. So this is the statement of symmetry. And can you see that this Q is now coming to the right of F? In objectivity, the Q was coming to the left of F. And that was simply because you were applying Q later on. But here you are applying Q earlier. Therefore, Q comes to the right and F comes afterwards. Okay? And and then you can define isotropy group. So isotropy symmetry group. So for isotropy symmetry group, let us say I say it is G. So this is all rotations in 3 dimensions, or it is the entire SO3. So for isotropy symmetry group, this Q here can be any rotation. So you see, we are defining symmetry in the body through the statement of stored energy being the same. Can you recall the when we started, we said that either the response is the same for isotropic or the material properties are the same. But we are finally working out symmetry in terms of stored energy. But of course, this will lead to some definition about the response also, which we'll figure out just now. So are you guys having any problem till now in understanding?
By saying that the Q lies in the symmetry group of material,
Yes.
and we are equating the energy at x naught, which is F naught,
Yeah.
in the F1 and F2,
Yes.
deformation. So
Hmm.
basically, Q is making no sense. Means like it is making no difference in the different
Yes, exactly.
both the
Yes,
deformation.
correct. If Q were in the symmetry group, then it will make no difference to the body as far as energy stored is concerned. So that's the
But
statement.
sir, here we are only considering the energy at point x naught, the
Yes,
energy, and not the entire body. So how are we taking
exactly.
considering Q for the entire body?
Yeah, we can see we just did a deformation process, a second deformation process in which you had applied Q to the entire body. But as I told you, the symmetry of a material property is a point property. It varies from point to point. It is possible that at a point in the body the material is isotropic, but at some other point it becomes anisotropic. So symmetry varies from point to point. Therefore, we can never make energy stored same at all the points. Of course, if the body is isotropic at all the points, then the energy stored will be the same at all the points, provided the deformation F that you are applying is such that F1 and F2, you see this F1 and F2 thing. So this and this, f of x naught and f of z naught, this should be the same. Then only it can be the same at all the points, which is possible if your f is constant. If big F is constant, then f of x naught will be equal to f of z naught, right? So if you apply uniform deformation to a body, then only you can make the energy stored same at all the points, provided Q is of course in the symmetry group. If the deformation applied is such that it is not a uniform deformation, that means the deformation gradient is varying from point to point, then you can never make energy stored same at all the points, irrespective of even material being isotropic. See, this is what we have learned from mathematics. Is that okay?
Yes, sir.
Sir, excuse me, sir.
Yes.
Sir, when you said while comparing F1 and F2,
Yes.
that so we found that uh, at x naught we are at least we found that the fx naught are same, not the q part. So then you said that now we can come at the physics and then you said the second statement according to ms, if the stored
Yes.
energy density this will be same. So why
Yes.
you went to the physics means like did you do the experiment or
Yeah,
or
I do the
and
experiment.
and and
Yes.
and and found that the W at F naught will be equal to W of F naught Q.
Well, actually,
So suppose
through
and
experiments, it is very difficult to measure energy stored. It is very difficult. So in experiments, they usually measure the response. That means the stress generated in it. But this was all
okay,
theoretical. If you could somehow measure energy stored, then you measure the energy stored in the two cases, and it will be the same. And if it turns out to the same, that means the Q is in the symmetry group of the material.
and sir, if the both are not same,
Then Q is not in the symmetry group.
then material will be anisotropic.
Well, it's so here we are just talking about symmetry group, whether Q is in
Okay,
the symmetry group or not. And certainly for isotropic, it has to be for all Q. And if it is not for even one Q, then it is not isotropic, so it becomes an isotropic, obviously.
okay. And sir, one
Yes.
last question. This Z will be a tensor or vector?
Sorry, it is a vector. I'm sorry. Yeah, thank you for reminding. So
Yes,
this
sir, because
is
all throughout we have used this tensor.
throughout I have used this. Let
Yes.
me check. Yeah, yeah, it's a point, no? So therefore, it's a vector. Anywhere else? Yeah, here also. Okay. Yes. Others also having some query? This is a really, really difficult topic,
Hello,
and
sir.
I really want to, it's nice that this is getting saved, so I can any student if he comes to me and says, "Tell me about symmetry," I will say, "Okay, why don't you go to this lecture?" So that will, it will remove burden from my. I mean, I will be burdenless then. So it's good that you're asking questions. Yeah.
Hello, sir.
Yes.
Um, so, as per this, uh, what we have derived at a point, if the energy density is same in the two process, it's about x naught. That is a point about which we are rotating the body.
Yes.
Rotating
Yes.
the body. So if energy is stored, energy density is stored is the same. So we are able to say that that rotation belongs to the symmetry group. That is like a
Yes.
mathematical way of saying, right? The
Correct.
symmetry
Correct.
group. So
Yes.
uh, if we take another point, like another x naught, and
Yes.
do the rotation, and there we got that q is belonging to symmetry group, but then
Yes.
but we are not getting that all rotations in three dimensions. Like the isometric symmetry group is all rotation, but
Yes.
if we are not getting that, so will that mean that at that point in the same body, it is anisotropic? Will that come?
Yes, exactly. Yes, yes. This is what it will mean. So this statement is for that particular X naught only. So symmetry group varies from point. And through this process, we are able to find out symmetry group only for that X naught. If you want to get symmetry groups at some other point, then you have to rotate the body about that particular point.
Okay, sir.
Yes, very good.
So,
Yes,
for say a transversely isotropic material, the symmetry
yes,
group will be about that rotations about that axis.
yes, exactly. All rotations about that axis, and it is denoted by SO2. They say it's SO2 rotation about that axis, but all such rotations it's noted by SO2.
Okay. So,
Yes. Okay, so this was a statement based on energy. Let us see what we can say through stress. You remember, even for objectivity, we started with the statement of energy, but then we also had a statement based on Cauchy stress tensor that sigma will change to q sigma q transpose. Remember? So here also we want to work that out. Can you tell me before working out itself what will that be? Can someone tell me? So you have to really think of it. So again, I'm just focusing on that point x naught. At that point x naught, just think of what it should be. If Q is in the symmetry group, then energy stored is obviously the same. What can you say about the Cauchy stress sigma? When the body gets deformed finally, what will the Cauchy stress sigma be in the two processes at point x naught? I mean, corresponding to point x naught. What do you think? the tensor sigma, not the components of sigma. I am talking about the tensor sigma. Okay, if you're not able to think about it, then let us first work out the mathematics and maybe we can then come back to the physics. So from here, to talk in terms of sigma, we obviously have to take the gradient with respect to f, isn't it? So let us do that. So our statement is that W of f is equal to W of fq. So let me take the derivative with respect to Fij, for example. So this is going to be del W over del Fij at f is equal to del W over, say this is del, so this entire thing, if I say suppose m, so del m I k into del m I k over, well no, so this is del m kl and here it is kl over del fij, right? Do you agree with me? And what is mkl? So m is fq, then mkl will be equal to fkp into qpl, right? Simple product. So you can come back here and this becomes del w over del mkl and then del mkl by del fij. So that's delta ik into delta pj into qpl, which is del w over del mkl. Well, sorry. So this is so you have ik. So k becomes I. So it is il, and then here pj. So p becomes j. So it is q j l. Are you with me? So we can now come back to the tensor form. So the left hand side, we all know that this is the Piola-Kirchhoff P at F, whereas on the right hand side, del W by del M is also P, right? But at FQ into, and you see here, it is IL into JL, or it will be IL into Q transpose LJ. So this becomes Q transpose. Are you with me here? So this is the statement of symmetry in terms of first Piola-Kirchhoff stress tensor. So if you can measure the Piola-Kirchhoff stress, then the symmetry group would just say that P of F is equal to P of FQ into Q transpose, or just that the Piola-Kirchhoff in the first process will be equal to Piola-Kirchhoff in the second process multiplied by Q transpose. So that's the statement of symmetry group. Now let us try to work it out in terms of Cauchy stress. So we know that sigma is equal to, is it 1 over determinant of F into PF transpose? Am I right? Anyway, so sigma 1 is then 1 over determinant of f into p of f into f transpose, right? Whereas sigma 2 will be 1 over determinant of fq into p at fq, right, into fq transpose. Now, using this thing here, and then also the determinant of fq is determinant of f into determinant of q, but then determinant of q is 1 because of rotation, so it becomes 1 by determinant of f into, this is p into f, p of f into q. Is that okay? I hope I haven't made any mistake.
Yes, sir, it is true.
Okay, but it looks like I have made a mistake somewhere. Um, anyway, I'm sure that I have made a mistake. Or maybe not. Sorry. No, I have not made a mistake. So, and then this is now Q transpose into F transpose, right? Now this goes away. So you get 1 over determinant of F into PF into F transpose, which now if you compare with this is same as sigma 1. Okay, so you see, magical, that the symmetry group just says in terms of Cauchy stress sigma 2 is equal to sigma 1. This is what the statement of symmetry in terms of Cauchy stress. Something that, we started with initially. Can you recall that here we're trying to compare sigma xx, sigma yy, and we said that if epsilon xx and yy are same, then sigma xx will be equal to sigma yy. So this is, so you get the same stress tensor. So the Cauchy stress tensor is the same in the two processes. This is quite magical. At point x naught. Now can we go back to physics and see that it should be that if it is if Q is in the symmetry group, it just says that sigma should be the same in the two processes at x naught. And that's also, and why it is so? Because this is what we have been thinking of symmetry, material symmetry, that response has to be the same. So finally, when someone goes and measures the actual stress in the body, the stress components, stress tensor itself is the same in the two processes.
And we have defined material symmetry now in terms of the first Piola, Kirchhoff, and Cauchy stress tensor. So, are we linking this to the isotropy or anisotropy symmetric group?
No, it just says that if Q is in the symmetry group, then this is going to hold and this is going to hold. Now, whether it
Okay,
is
sir.
isotropic isotropy or transverse isotropy, it depends on what all Q are there. If it holds for all Q, then it becomes a isotropy symmetry group. If it holds for only special Q's such that its rotation about one particular axis, then it's a transversely isotropy group. And likewise, you can think of several other groups. But
Okay,
for
so
a
this is
particular
a
Q,
statement.
yes, yes.
Okay, thanks.
Any more query? Now let us try to combine both objectivity and symmetry and see what we get. So objectivity tells us that W of F has to be equal to some phi of C, isn't it? Because W of F means it has to just depend on U, and U is square root of C, so it is finally dependent on just C, where C is F transpose F, the right Cauchy Green tensor. Now let us see what happens to W if we further incorporate symmetry in it. So symmetry means W of F is equal to W of FQ, right? So how does C change here in this case? So C is going to change to FQ transpose into FQ, right? Because that's the new F, which is same as Q transpose F transpose F. So that's the original C into Q. So this implies that phi of C has to be same as phi of Q transpose CQ for all Q in symmetry group of the material. Okay? And if it's an isotropy symmetry group, so you see, this is the statement of energy. See, you are getting more and more restrictions on forms of energy. So energy cannot be anything. It must satisfy this property if Q is in the symmetry group. So you remember in the beginning I told you that there is no physical law which can tell you the exact form of energy. And that is very true. But at least using objectivity and symmetry, you have been able to provide some restriction to what energy has to look like. So any energy form, whatever it is, it must obey this relationship if Q is in the symmetry group of the material. Okay, now let us work in particular for the isotropy group. So isotropy symmetry group. So here Q has to be all SO3, all rotations. Now look at the statement of energy, the way it is appearing. Phi C equal to phi Q transpose CQ. Now this would also be equal to phi of minus Q transpose C minus Q, isn't it? You can put two minuses. You get the same thing. So this means it holds not only for Q but also for minus Q. Now if Q is in the rotation, then minus Q is a reflection, because determinant of Q will then be minus 1. And then so just for isotrope, I mean for symmetry group, we could also then enhance this SO3 to O3. If it's an isotropy group, then SO3 can be enhanced to O3, which contains. See, don't be worried about this big names SO3 or O3. It's simply that it contains rotation as well as reflection. Or all orthogonal matrices. All orthogonal matrices or tensors having determinant equal to plus minus 1. Okay? Now you see this energy has to hold for all Q, this equivalence. Then obviously it will put some restriction, isn't it? The energy cannot be just like anything. For example, you cannot have an energy such that phi of C is equal to C11 plus C22 plus C33 and keep on going up to C. If I write it like this, a double over ij Cij. This cannot be the form of energy. Why it violates? This is not correct because it violates this relationship for all Q. So basically the energy can only depend on those quantities which are invariant under this operation. So it can only depend on those combinations of C which are invariant under this operation. So we have to find the invariance of C. Under the operation Q transpose CQ. Okay. So by invariance, I mean find out some particular combination of C which does not change even if C changes Q transpose CQ. Can you think of something which will not change?
Eigenvalues.
Eigenvalues, very correct. It turns out the eigenvalues do not change. But can you think of something more? Can you say again?
Determinant.
Sorry?
Trace and determinant.
Determinant, yes. For example, look at determinant of Q transpose CQ. Determinant of Q transpose. This is same as determinant of Q transpose into determinant of C into determinant of, which is same as determinant of Q, because Q transpose is same as determinant of Q, and then whole square into determinant of C. But Q being orthogonal, the determinant of Q will be plus minus 1, so this finally becomes determinant of C. So determinant is invariant. Another important property is the trace. The trace, for example, look at trace of Q transpose C. So suppose I say M is equal to Q transpose C. then what is MIJ? MIJ will be Q K I, because Q transpose. So it is Q transpose I K into C L into Q L J. That's MIJ. And what is trace? Trace is simply MII. So what is this equal to then? Q K I into C K L into Q L I. Okay. Now, what is this then equal to? You can say it is Q K I into Q L I into C K L. But Q being an orthogonal matrix, you see, what are these two?
Delta KL.
And why it is delta KL?
Because Q is orthogonal.
Just a second, let me take a call. Hello? Hello? Yeah, you see, this is QKI is the kth row of Q and QLI is the lth row of Q. So you are simply taking the dot product of kth row and lth row. And the rows are orthogonal to each other. So this becomes delta KL into CKL, which is same as CLL, which is trace of C, right? So you have proved that this is same as trace of C. So trace is also invariant. Do you remember in your undergraduate course you had learnt about some invariants? For when you're doing the stress transformation, did you find out some invariants?
Yes, sir.
What were they?
Trace, determinant, and the sum of determinants of 2 cross 2 matrices.
Some of demand. Yeah, but do you remember in terms of I2 and one, sorry, how do they call it? 1 sigma, 2 sigma, 3 sigma. Is that how you do you remember something like that? First invariant, second invariant, and third invariant. So
First
there is another
invariant.
invariant. Anyway, there is another invariant. So first invariant is trace, third is determinant, and second invariant is the one that you did in minor exam. You remember in your minor exam, the last question, you had to find out the derivative. So that's the second invariant. So we denote them by IC invariant, 2C and 3C. IC is trace of C, 3C is determinant of C, and 2C, if I remember correctly, it is half of IC whole square minus trace of C square. I think this is what it was. Is that okay? Can someone recall? Which is half of IC whole square minus I of C square. I may be missing some factor here. Can someone confirm?
Yes, sir, it's correct.
Okay, this is fine, Rawson? Yes, hello?
Yes, sir, it's fine, sir. It's right, sir.
Okay.
Hello.
Yeah. Oh, all right. All right. Thank you. Okay, so this is, so this means that the energy will finally, so phi C. So we started with WF. So let me just make it more clear. So we started with WF, which was most general, which became phi C through MO. And then using isotropy, it becomes some other function, let us say phi hat, but only of the invariants. And it turns out there are only three independent invariants, IC, 2C, and 3C. So the energy finally only depends on these. This is the final form of energy for isotropic, non-linear isotropic material. So this is for non-linear isotropic material. Okay. So with this, I will end the class for today.